Hello, my name is Ethan. This is Sandy Ruda, and this is Viswa. We are presenting on Neuro Symbolic Deductive Reasoning for Cross-Knowledge Graph Entailment. So, do a little background first. The idea of deductive reasoning is the process of reaching a conclusion given a set of premises. So, for example, we have premise A, which is all dogs are mammals. Premise B, which is mammals are warm-blooded. Therefore, you can derive that all dogs are warm-blooded. And this happens by applying a common set of rules of inferences or a schema, which is provided by usually classical logic. And some examples of well-known rules of inference are modus ponens and modus tollens, where respectively modus ponens is P implies Q, therefore P entails Q, and modus tollens is P implies Q, therefore not Q entails not P. And an argument is valid if it is not possible for the conclusion to be false given the premises are true. And additionally, an argument is sound if it has a valid form and the premises are true. And to add to that, a hypothetical syllogism is a valid argument form. And we have an example here, which is P implies Q and Q implies R, therefore, or which implies P implies R. And now to touch on knowledge graphs, here we have an example of a knowledge graph, which is pretty intuitive. As you can see, a knowledge graph is essentially a graph of edges and nodes depicting some semantic relationship or some semantic relation between all the nodes. So for here, we have in the bottom left, we have dogs, which is an animal, which you can infer from that an animal is a living thing, which you can infer from that a dog is a living thing based on the edges connecting. And now we have the introduction of knowledge graphs. So a knowledge graph, also known as a semantic network, is used usually to encode knowledge and manipulate massive amounts of data. Knowledge graphs are generally used by companies to encode relationships between their relevant entities. So for example, social media companies use knowledge graphs to encode relations between their user networks. And entertainment companies, such as Netflix, for example, uses knowledge graphs to supplement their recommendation systems. Additionally, KGs can enable a wide range of tasks, such as knowledge representation, which I just mentioned, classification and reasoning. And the World Wide Web Consortium, which is a conglomerate that was a committee that standardized a family of knowledge representation languages, which is now used. For the main three are the web ontology language, which is OWL, the resource description framework, which is what is used in our paper, which goes by RDF, and then additionally the semantic web rule language, which is SRWL. And now I am going to pass it on to Aniruddha to discuss the knowledge graph embeddings.
So let's get to the machine learning part, right? Like what we've been waiting for right now. So we have the first option of embedding is a syntactic normalization, which will come to it later because this is the main embedding method that is being used by the authors. But before that, we just described some more, machine learning forward method of embedding. So first we have trans E, where you basically imagine the relation, the subject and the object to be in vector spaces. And since we all know that the subject leads to the object is a unary relation or a binary relation, you can lead back. So you can express it as a vector addition, as you can see here, the head, the tail, and the relation space. Sorry, it's not that clear. The main assumption of this method of embedding is all of them have the same dimensional vector subspaces. So the next slide, please. And obviously, we know that it's not possible, right, to be in the same vector space for all the relations of entities and the objects and predicates. So we have an entity space which may or may not be same with the relation space, and we have projection in the form of matrix of a relation space of k by t, where t and k are not equal, that is the size of the entity space and relation space respectively. And then take the vector addition. So next slide, please. We'll go to the overarching architecture that is being used by the authors. Note please, the trans E and the trans R is not used by the authors. It's just a intuition of how other embeddings might work. Now we'll go to the architecture of the memory networks. As you can see, there are not really neural networks present here, right? Because a neural network is actually only present in this region over here, the output module and the response module. And these two modules, these are your feature conversion or the input feature converters or encoders. And G module is the one that updates memory given new inputs, right? So we'll go to the next slide, please. Yeah, it's just what I said earlier is written. So the I is input feature maps, converts the input features into the features that can be learned by the machine. Generalization is for memory updates. Output feature map produces new output, given the new input and current memory state, and the response. The response, interestingly, the authors have a novelty in the sense that the model can be anything. It can be RNNs, it can be LCNs, it can be attention, it can be MLP. And also it says it can give a textual response or an action. So it actually opens a lot of avenues and a lot of research, a lot of machine learning avenues. It can be used for classification or textual sequencing or any kind of reinforcement learning setup. So that preludes to the next slide, please. The inference of the memory networks. So this is not the authors of the actual deductive reasoning paper. This is the work of the authors of the memory networks. And here, these are examples which can be the simplest examples that can be used as the outputs and inputs and response models. So first, we obviously have a very simple explanation of the argmax of a scoring function. That is SO. We just take the maximum similarity or the maximum score of any given memory. And for the next iteration, we can use a kind of a recursive function over again for the scoring. And the simplest response again is an argmax with the scoring between the weights and the memories of M01 and M02 for, say, let's say we have two iterations, for the two iterations and the input. And scoring function itself is a very general explanation of the authors of memory networks, which is given by the conversion of the raw inputs into feature space, the conversion of the outputs in the feature space, and the matrix of size something k by d, where the d is the number of the feature space and k is the number of feature space and d is the dimension of the feature spaces. And there's a little bit of ambiguity here because they use u for embedding as well as the model parameters, but yeah, just be aware of that. Next slide, please. So yeah, here when we talk about the learning of it, the problem comes that the UO and UR are actually the parameters of the model, not the parameters of the features. And in their example, where they use it for question answering of text, not exactly logical reasoning, they use margin ranking loss, and it's trained by vanilla SGD and vanilla backpropagation. Nothing really flashy about that. Just the thing about margin ranking loss is that it ranks certain memories according to their importances, and it sums over the memories which are not the correct result. Next slide, please. And now we come to logical entailment, the problem that we're formulating in our actual paper. So any logic language or any logic system basically comes with an entailment relation where you have the theories, which is a set of all the logic formulas, and the formulas, which is a subset of their logic formulas. And you basically query the logic that if F is entailed by T, if F is concluded by T, or the theory concludes the formula. So what the authors do is they assume that the given knowledge graph is the theory and the queries are the formulas. And whenever they ask a question through the query, they're asking whether or not the query is entailed by the knowledge graph. And And how do they formulate that? How do they know that the answer is entailing? So they basically just take it as a classification. They take the query and they classify it to yes or no labels, or 0 or 1 label. That is a binary classification. So this is how they reach the conclusion if a formula is entailed by theory or not. Next slide, please. And now we are going to this actual embedding that is being used by the authors in a paper. So deductive reasoning requires a model or a naming agnostic outlook. That is, it should not be interfering. The name should not be interfering with the learning of the model or the reasoning of the model. Just like in the last lecture, Professor Samari said in this discussed paper that the database is generated by the relations that are existing in the given data set, right? So here it's slightly different outlook. The embedding is done in such a random manner that all the variables, that is the predicates, the subjects and the objects, or the relations, they are renamed randomly so that there is no fixed namings for that. It is completely named randomly. So it helps in forgetting the relevant label names and assists in transfer learning from one KG to another. So next slide, please. Now we come to the model, actual model that is being used by the authors. So as I said, there is an inputs module which converts the converts the triples into a normalized triple. And you store that in the vocabulary, that is the G, that is being updated with every new input. There is the I and the G, and this is the output response. There is the softmax, which gives you a yes or no, and here is the thing that you are being classifying as the queries. So next slide, please. Just a bit. Next slide. The last slide. Yep. As I said, the R could be anything. Right now, it's an attention dot product, which is not explicitly said in the paper, it is MLP, but a little bit of digging in the GitHub repository will give you the answer that they are using linear networks, and also in their experiments they use linear networks without any bias, because the bias doesn't really play a role in the dot product because it's an additive term. And it does multi-hop attention, which basically means that it is doing self-attention, but it's allowed to jump over entries. So basically, it's just a short diagram, like if A and B is leading to C, normal attention would be attending over A and C, and A and B. And if suppose attention, like let's say attention, and if there's another node, say D, it will be still attending over A, D, and AB. That's your vanilla self-attention, right? We're just single hop, right? And in multi-hop, we're just allowed to do this. We're allowed to do this directly to D and C. So next slide, please. So these are just the mathematical descriptions. Like the component is defined as an N by D tensor, where the N is the number of triplets and these dimensions are minutes. A memory vector shows two continuous representation of M and Ci obtained from matrices A and C with size D by B. These are the vocabulary. Query is embedded by a matrix P to obtain internal state U. So A and B and C, these are embedded to syntactic normalization. So all of these are unique, and to solve the problems of leakage of the query into the input, we have no kind of leakage anywhere. So this, and this, these are all unique. So next slide, please. And next slide, yeah. So obviously, some kind of non-linearity has to be there. So softmax is the key to go for probabilistic non-linearity. And the internal states, the formula is slightly shifted. I guess internal state of the internal state of the query updates on next hop, that's that UK plus 1 is equal to UK plus OK, and O is the weighted version of the contents of the memory with the probability of it. So next slide, please. So the cross-key entailment will be explained by Vishwa.
So the main purpose the author wants to do is they want to develop a model which can be used for transfer learning on other databases, other KDs to see how it can be generalized over different needs. So in this, the framework they are using is the resource description framework, which is RDF, which is a form of representing the knowledge graphs. And in these RDFs, we have triplets, which is represented by triplet, where the E1 R and E2 are the triplets, and E1 is the subject, and E2 is the object, and R is the relation. Let's say, for example, Ethan gets Anirudh is a sentence. Ethan is a subject, and object is Anirudh, and the relation is given. So that's how it's represented. And so in this syntactic normalization, when they normalize these triplets, they do it based on position. So when I say position, the next slide. So when I say the position, let's say an element J in a triplet, I, where each of the element is represented, the triplet is represented by Dij. So when you calculate the position of each triplet, you have this factor, which is calculated using this, where J is the element you are calculating the position weight for, and K is the number of hops that you are using for this experiment, and 3 is the number of elements in the triplets. So this LKG is a column vector. So for hop 0, it's L0 for each element, and from the next hop, it is L1 of each element. And this is how you calculate the position vectors of a triplet. So if a triplet is reversed, the position vectors is changed because in the first triplet, the subject can be an object in the next triplet.